Hey guys, I'm Brandon Hemeyer, and I'm going to be teaching you about lasers today. It's a really cool topic. I've definitely enjoyed learning about it, so hopefully you enjoy the lesson. So I'm sure that for everyone, hearing the word laser brings a lot of different things to mind. You've got the science fiction portrayals in Star Trek and other movies. You've got your classic Dr. Doofenshmirtz from Phineas and Ferb and his many devices, or maybe you're just thinking about playing with your cat. All very entertaining uses of lasers, and one or all of these might be more exciting to you than the reality of lasers for now, though hopefully I can change your mind on that. So laser actually stands for light amplification by stimulated emission of radiation. That might just be a jumble of words right now. It's kind of a lot. Hopefully it's going to start making more sense as we go on. And actually, before we dive into the design of lasers and some of the applications of them, there are a few other topics that we need to hit really quickly just to get a base understanding that will help us as we go forward. So the first of these topics that we need to go over is the Bohr model of the atom. So what we have here on the left is this model of an atom with a nucleus at the center, and then you've got, in increasing distances from the nucleus, these different levels of energy. So n equals 1, n equals 2, those are increasing levels of energy. And what the Bohr model postulated was that electrons can exist only at those specific levels. So they can jump between them, they can increase or decrease in energy levels, but they can't actually exist outside of those levels. So an electron can be excited and it can jump up from, say, level 2 to level 3. And then what we've got here in the diagram is that electron decaying and going down in energy from level 3 to level 2. And when that takes place, energy is released. And the form that that energy takes when it's released is the next topic that we need to dive into really quick. And that form is a photon. So all of you are probably aware that light takes the form of a photon. However, that wasn't always the case, of course. There was a time in history when the form that light took was a topic of serious debate. Back in the 1700s, you had those arguing that because light exhibited the properties of a wave, that it must be a wave. Others who argued that it exhibited some particle attributes, and therefore it must be a particle. As it turned out, of course, both were a little bit right, maybe a little bit more wrong, and it was eventually understood that light is emitted as a photon. So we can think of a photon as this little packet of energy exhibiting qualities of both waves and particles. Important to note that photons have this intrinsic energy about them, and that energy is related to their wavelength. That equation is shown on that last bullet point there, E equals hv, h being Planck's constant, and v being the wavelength. So now, having this basic understanding, kind of an introduction to the Bohr model of the atom and light in the state of a photon, we can dive a little bit more deeply into absorption and emission here. So on the top diagram that you can see, that's representing absorption. On the left-hand side, you can see that squiggly line kind of entering the atom. That is a photon of light. As it is absorbed by the atom, you can see that the electron jumps from energy state 1 up to energy state 2. It's become excited and has increased in energy. Of course, it's not going to just stay at that excited state continuously, and you can see in the diagram below it, spontaneous emission that occurs. So you've got an electron that's excited, it's at energy state 2. Over time, it's going to decay or decrease in energy as it moves down from energy state 2 to energy state 1. You can see that squiggly line leaving the atom. That is a photon of light being released. So over time, electrons that are at an excited state are going to release that energy in the form of a photon, and that's just kind of going to fly off in a random direction. However, spontaneous emission isn't the only way in which an electron can decay and release that energy. You also see the bottom diagram shows us stimulated emission. So these electrons, we can think of it as these electrons kind of like to go with the flow. So if you've got an electron that is already close to decaying and you've got a photon that passes by that's at a similar level of energy, that will cause stimulated emission. And in that case, the photon isn't just going to fly off in a random direction. It's actually going to be, with that stimulated emission, it's going to leave in sync with the photon that was already passing by. So then you can see that the two of those, their wavelengths are kind of lining up as they both leave in the same direction. Again, important to remember that that occurs when a photon of a similar energy level and therefore similar wavelength is passing by as the electron is close to decaying. So this concept of stimulated emission really starts to open up some more possibilities, and it's what makes the creation of a laser and a traditional laser beam that you might think of a possibility. So what we get here, you have, of course, the spontaneous emission of photons that's occurring all the time in random directions, and then in some cases, that will result in stimulated emissions as that photon passes by an electron that's already in that excited state and ready to decay at a similar energy level, then you get stimulated emission. And as those photons continue moving in sync, they'll stimulate further emission of photons. And you get this kind of amplification, as it says. You get a chain reaction that increases the number of photons, increases the concentration of them, all moving in the same direction, until the point where you have this beam that's actually visible, a visible beam of light of all of these photons that have the same wavelength. That's why we see that solid color of a laser. And of course, this process is also where we get the acronym for laser: light amplification by stimulated emission of radiation. So this really is how we get a laser beam. Now, a reasonable question that might arise is, seeing as spontaneous emission is occurring pretty regularly, and that opens up the possibility of stimulated emission, then why don't we see the stimulated emission of spontaneous lasers? Why don't we see lasers being emitted naturally as photons are emitted spontaneously and then stimulate further emission of photons and create that chain reaction? And the answer to that question is that the concentrations of excited electrons that are required to actually get a visible laser beam are much higher than what we would find occurring naturally. We know from our chemistry classes that electrons prefer to be in the most stable state, and that would be the least energetic state. So you're not normally going to find these high concentrations of excited electrons all at a similar energy level, decaying in order to create this beam of concentrated photons that is required for a laser. And that requires a much higher concentration and one that has to be created artificially. And of course, that's exactly what we do in a laser. So here we have the basic design of a laser. You'll see there what's called a pump source, which is essentially that can take many different forms, but really the whole purpose of that is that it is exciting the electrons that you see there in the very middle, that medium there in the middle. Those electrons are being excited by the pump source, and as they become excited, of course, with time, then they're going to decay, and as they go back down to a lower level of energy, they're going to spontaneously release a photon of light. And so as that's happening, you're going to see lots of spontaneous releases of photons in just random directions, shooting out in all directions. And most of those aren't going to be particularly useful. But every once in a while, you're going to have a photon that is emitted in parallel with that medium. So then, as it moves through the medium, it will then cause the stimulated emission of more and more photons, with so many of them being in that excited state from the pump source. And as they move in that parallel plane, you can see that we've got mirrors on either side. So that first time through, that single photon that gets released might not create too much of a chain reaction, might not release too many other photons and stimulate their emission. However, with the mirrors on either side, those photons in that plane are just going to be continuously going back and forth, and causing more and more photons to be emitted. So then, as you can see, the two mirrors are labeled a little bit differently. On the left, we have a highly reflective mirror, so every photon that hits that is just going to be shot back into the medium, causing more and more to be released. And then on the right, we have a partially reflective mirror. So most of the photons that hit that are also going to be reflected back into the medium, continuing the reaction. However, you are going to see that laser output that's coming out, as some of the photons will pass through as it is only a partially reflective mirror. It's not going to reflect back all of those photons. And that's why we see this continuous output of photons, of light, of course, as we see it. Continuous source of kind of piercing light, as you would typically think of when you think of a laser. So that's the basic design of a laser. And here we have listed just a few of the many practical applications of lasers. Obviously, the uses of lasers go far beyond just the few that I've been able to list here, but I found these interesting. Lasers are used in the medical field as a non-invasive option for cancer treatment. They're used in the dental field as they can alter the soft tissue of the teeth. They're used in communications. They're used in the military for communications and for range finding. Not quite at the point of laser guns at this point, I don't think. But the list goes on from everything from welding to hair removal. Just many different applications of laser technology. There's a good chance that there's an application for this technology in whatever field you might be going into. So hopefully I've piqued your interest just a little bit, and hopefully you've been able to gain a better understanding of the mechanics behind lasers and some of the uses for them. Thank you for listening.